subtopic number 2, which is on radioactivity. Right, so in this subtopic, you have to be able to explain what is alpha, beta plus, okay, so alpha, beta plus, B minus, B pula. B kenapa to? It should have been beta. Okay, beta minus and gamma decays, right? So in this in this one, you have to know that radioactive decay is spontaneous and random process, introduce neutrino and antineutrino. Okay, and then you have to state and use decay law. That's the formula there. This one, define and determine activity and decay constant, consider decay curve, use these two equation and define and use half-life. Okay, so calculation basically yang ni semua ni calculation now. Oh my god flop sure. Okay, so I'm just looking for my this one. Alright, so radioactive decay is defined as the disintegration of unstable nucleus to a more stable daughter nuclide with the emission of either alpha particles, beta particles, and gamma ray. Either N. It's N with the emission of these three. So it is a spontaneous and a random process. So random means that the time of decay of each atom cannot be predicted. Spontaneous means it happens by itself without external stimuli. Okay? Stimuli. The decay is unaffected by normal physical or chemical processes such as heat, pressure, and chemical reactions. Okay, so there are three types of nuclear radioactive decay that emit three types of radiations. So we have alpha, beta, and gamma. So for the alpha radiation, it has a charge of positive 2 electrons and a nuclear number of 4. The symbol of an alpha particle is this here. It has the least penetrating ability and can be blocked by a sheet of paper. Its motion is deflected by magnetic field and electric field. So the transmission of this particle can be blocked just by a sheet of paper. Okay, and then for beta radiation, it has the same mass as an electron, can be either positive or negative, has the moderate penetrating ability, and can be blocked by a few millimeters of aluminum ataupun a sheet of plywood. Okay. Similarly as alpha, its motion is deflected by a magnetic field. Magnetic field lah. Electric field teda. So symbol for positron is this one here. So any positron lah. This one is positron because it's positive. This one is negatron because it's negative. Okay, so we have gamma radiation. Radiation is a high energy photon. It has no charge and no mass, and it has the most penetrating ability, a few centimeter in lead lah. Okay, so it is not deflected by any magnetic field. Okay, so dia boleh kena block oleh a 1 meter of concrete sahaja, macam itulah. Okay, so gamma decay dia occur dari high energy atom, lepas tu dia there is no change to the protons or neutrons, tapi lepas tu the high energy wave is released lah time gamma decay. So the comparison of the properties are this shown here. So basically what you need to know is I need to fix this. Okay, so the deflection by electric and magnetic fields is only for alpha and beta. Gamma is unaffected. The ionization power for gamma is weak, but however the penetration power is the strongest, and all three of this has the ability to affect a photographic plate and produce fluorescence lah. Okay, so this is the path lah, deflection of alpha, beta, and gamma. Kalau alpha, they deflect to the negative plate. If beta, they deflect to here. Sama juga. This one is actually gamma. Okay, tapi untuk kalau kita tahu gamma ray, dia tidak deflected by electric field and magnetic field lah. This is E sepatutnya. I believe that should be gamma. I'm just gonna fix it later lah before I upload. Yes, it should be gamma. I don't know why I write E there. Okay, right. Okay, so that's that. So this is just the comparison lah in the penetration power of each of alpha, gamma, alpha, beta, and gamma. Right, so the strongest one is the gamma ray lah yang saya sebut tadi. Okay. Alright, next radioactive decay. So we have radioactive decay. Sama juga dia ada alpha decay, beta decay, and gamma decay. Okay, tiga-tiga ni ada decay dia. So untuk alpha decay, it will emit an alpha particle that and the helium isotope will lose 2 protons and 2 neutrons. Okay, so the general form of alpha decay is shown here. This is the parent, this is the daughter, and this is the alpha particle. Okay, so kalau kita tengok di sini, macam ni, this is the parental nucleus kan, this is uranium, and then dia after decay event dia jadi the daughter nucleus jadi thorium, and then this is the emitted alpha particle. Is this thorium? I don't know what's the name, but that's that lah. So it is a nuclear transmutation process in which one of the element is converted into another element. Okay, so dari uranium dia jadi this one. I believe it is maybe, I'm just gonna Google it quickly. So TH is maybe it is thorium. TH element. What is that? Thorium. Yes, correct. It is thorium. This is the alpha particle, and then this is the energy release. So it releases, the energy release is in a form of kinetic energy. So this is the formula lah, Q delta mc square, where delta m here is the mass difference before and after decay. C is the speed of light lah. So if all of the masses is in atomic mass unit, sama juga kita boleh darab dengan 931.5 mega electron volt. Okay. So for beta decay, we have two types. We have negatron and positron decay. For the negatron decay, it occurs when an unstable nucleus has too many neutrons. Okay, there are too many neutrons compared with the number of protons. So through the beta decay, negatron decay, a neutron is then converted into a proton, and it will then create a more stable nucleus. So macam ni lah, the neutron ni, salah satu neutron ni dia akan convert jadi proton. So that allows for a much more stable nucleus lah. So this is the parent, this is the daughter. Basically dia punya proton number tambah 1 sebab dia convert jadi proton kan, the neutron tadi. And then dia akan release negatron, this is the emitted negatron, and then this is the anti-neutrino. Okay, so this anti-neutrino ni exists in order to obey the law of conservation of energy and angular momentum lah. Okay, lepas tu so this is an example of beta decay lah. This one is the negatron, this is the anti-neutrino. Okay, so for positron decay pula, it occurs when an unstable nucleus has too many protons compared with the number of neutrons. So sekarang tadi negatrons dia terlampau banyak neutrons, tapi sekarang dia terlampau banyak proton. Okay, so through the positron decay, a proton is then converted into a neutron and will then create a more stable daughter nucleus. So one of the neutron ni dia akan jadi proton. Should be the other way around lah, sebab saya sudah cakap tadi. Let me just check ya. Yeah, nasib saya nampak this should be N lah. So dari proton dia jadi neutron. Lepas tu this one is the positron expelled. So this should be positron. Okay, sebab this is a positron decay. Oh, tidak payah ada minus ini pun okay. Tidak payah ada plus. But it's plus juga lah, it's positive juga, positron kan. Okay, so this is an example of positron decay. And This one shouldn't have any negative. I'm just gonna use red just so that I know I need to correct that. Okay? So, di sini dia akan lose 1 electron. Oh, ni saya copy paste dyan. Ito lah banyak salah. 7 minus 1 lah sepatutnya. Okay, so the atomic number of the daughter nucleus decreases by 1, but the mass number remain unchanged lah. Again, an antineutrino is again, another, banyak tu salah ni. Okay, so another elementary particle called neutrino is emitted in this decay lah. Okay, so sekarang tadi antineutrino, sekarang pula neutrino. Kenapa dia keluar? Just because so that it obeys the law of conservation of energy and angular momentum lah. So both this antineutrino and neutrino ni they have 0 electric charge and 0 mass. So it interacts very weakly with matter and is very difficult to detect lah. Okay, so that's that. And then for gamma decay pula, it is emitted when an excited nucleus jumps to lower energy level. Okay, so dari high energy level dia turun ke energy level yang lagi rendah. So this is high, tiba-tiba dia pergi low. So when this occurs, dia ada gamma ray. Macam tu lah. So very often a nucleus is left in an excited energy state after it has undergone alpha or beta decay lah. So that's why dia ada gamma decay. So this nucleus can then undergo a second decay to lower energy and to lower dia punya energy level by emitting a high energy photon. Okay, so they emit a high energy photon known as gamma ray lah. So the decay can be written as this one shown here. So dari excited state dia turun macam ni. So that is the gamma ray lah. Okay. Lepas tu, when a nucleus decays by emitting a gamma rays, the only change in the nucleus is that it ends up in a lower energy state. Okay, so it ends up in a lower energy state saja. Okay? Okay. Right, so that is on gamma ray lah. Untuk decay law, okay, so for decay law, it is for a radioactive source, the rate of decay is proportional to the number of radioactive nuclei present pula. Okay, so rate of decay is proportional to the amount of nuclei, and then this is the equation for decay law lah. So this is the rate of decay process, this is the decay constant, and n is the number of radioactive nuclei present. Sorry. So the negative here is telling us that the number of radioactive nuclei present is will decrease with time lah. Okay, so dia makin lama makin berkurang. Mestilah dia berkurang sebab dia tulis sini rate of decay. Okay, dia decaying, maksudnya dia akan makin lama makin berkurang. Okay, so that is on decay law. Untuk activity pula, it is defined as the number of decays per second that occur. Okay, so formula dia adalah A equal to lambda n. Okay, so again, this is the rate of decay process, this is n the number of radioactive nuclei present, and then lambda is the decay constant. So the SI unit for activity dia ada dua lah. Okay, bukanlah ada dua, dia becquerel actually. The SI unit is becquerel, but then another unit that is usually used is Curie ataupun CI. Okay, so 1 becquerel is equal to 1 decay per second. So basically this one is the SI unit lah, dia memang sudah dalam second. Tapi 1 Curie ni dia equal to 3.7 darab 10 kuasa 10 becquerel. So kamu perlu convert pergi becquerel supaya kamu dapat supaya kamu konsisten lah, supaya kamu konsisten with the SI unit, right? Okay, so from the law of radioactive decay, we know that the rate of decay process is equal to negative decay constant darab dengan the number of remaining nuclei. And the definition of activity is this one here. So when we did I write it somewhere there? And we know that n here is equal to n naught e negative lambda t. Okay, so when we substitute it into this equation, we get an equation for activity. So yang ini ni kita boleh kira the remaining activity after a certain time lah. So kita just boleh substitute di sini untuk cari activity at a certain time. Right? Right, decay constant pula. So from decay law, this is the law, we get that the decay constant is equal to the decay rate over the number of remaining radioactive nuclei. So decay constant is defined as the probability that the radioactive nucleus will decay in 1 second. So the SI unit is per second lah. So sekarang ni per second, bukannya meter lah, apa-apa lah. Tapi dia bukan, kirain dia bukan meter. Dia mesti dalam massa, okay? Okay, lepas tu dia vary from nuclide to nuclide, and then the larger the decay constant, the greater the rate of decay. So ini proportional lah kira dia, okay? So each nuclide has its own characteristics rate of decrease. Okay, so sekarang barulah kita tengok untuk number of radioactive nuclei present. Okay, with time t. Okay, so this equation here is telling us the number of nuclei present in a certain time. So kita just perlu dah masukkan nilai t lah untuk cari n kah, kita mau cari lambda kah, apa-apa lah. Okay, tapi this is one of the equation lah. Lepas tu, this integration of radioactive decays ni reduces exponentially with time. Okay, so this is the decay curve lah. So this is the number of remaining radioactive nuclei in a sample against time. Okay, this is, I need to fix this. Okay, the graph, this one yang bang. Okay, so from the graph, we know that the life of any radioactive nuclide is at infinity. Okay, so to talk about the life of radioactive nuclide, we are gonna refer to its half-life. Okay, so kita akan belajar half-life lah. So half-life ni apa pula? Half-life ni defined as the time taken for half of the radioactive nuclei to decay. Okay. So it does not depend on the number of remaining nuclei. So the units boleh juga kamu guna second, minute, hour, day, year. Basically depends on the unit of decay constant lah. Jadi kalau kamu half-life kamu guna hour, decay constant kamu pun mesti guna hour. Macam itulah. Okay. So how do we calculate the half-life? Half-life is basically equal to ln 2 over the decay constant. So the longer the half-life of a nuclide, the more slowly it decays and the smaller the decay constant will be. Right, so this is a chemistry punya formula, because sometimes they will only give you the molar mass and the mass. So in order for you to find the number of molecules, you have to times it with the Avogadro constant. Tapi I believe you can still remember this one lah. Okay, example 5, the half-life of the radioactive nucleus radium is 1.6 times 10 to the power of 3 year. What is the decay constant of this nucleus? Okay, decay constant. Right, so dia bagi kita apa? Dia bagi kita the half-life, which is 1.6 times 10 to the power of 3 year. I don't like it when the half-life is in year, so I prefer to change it into the SI unit, which is just seconds lah. So how do we do that? Is we're gonna times it. 1 year there are 365 days roughly, times with 1 day there is 24 hours, times with 60, times with 60. Okay, so kamu akan dapat 365, 24, 60, 60. So you will get around 5.04576 times 10 to the power of 10 seconds. So this is the half-life of radium. So sekarang ni kita boleh cari the decay constant based on the half-life. Sebab because the relation of half-life and decay constant is this formula, ln 2 over lambda. Sorry, my chair is annoying. Okay, so dari sini kita just substitute lambda, which is lambda yang kita cari lah. Okay, so I don't like it when I do that. Why do I keep doing that? Okay, lambda is equal to ln 2 t half. Okay, so dari sini ln 2 divide by 5.0404576 times 10 to the power of 10. So you will get the decay constant to be equal to 1.3737 to the power of negative 11 per second. Okay, remember this is not the usual wavelength. This is decay constant. Okay. Next, if a sample contains, so that is n original nuclei at t equal to 0 seconds, determine the activity at this time. Okay, so activity at this time, we know that A is equal to lambda darab dengan n node. Okay, and this is the original lah. This is the activity at t equal to 0. This is the number of nuclei at t equal to 0. So, substitute je lah. Dapat jawapan. This is 1.3737 negative 11 darab dengan 3 darab 10 kuasa 16. So, the activity at t equal to 0 is equal to 4.1211 times 10 to the power of 5 becquerel. Okay, remember the SI unit untuk activity is BQ, which is becquerel ataupun decay per second lah. Okay, so what is the activity after 2 times 10 to the power of 3 years? Okay, so kita perlu convert lagi lah yang T ni sebab kita punya decay constant dalam second, so everything needs to be in seconds. 60. So T is equal to 6.30 6.3072 times 10 to the power of 10 seconds. Okay, so that's that. Right, so if you are confused, 1 year is equal to 365 days, 1 day is equal to 24 hours, 1 hour is equal to 60 minutes, 1 minute is equal to 60 seconds. So kita perlu convert dalam seconds. Right, mana tahu ada yang confused tapi malu mau tanya nanti. Okay, so activity is A equal to A naught negative lambda T. So we are looking for A. This is 4.1211 times 10 to the power of 5. Salah. Lambda is 1.3737 negative 11. Tidak muat. Have to do it somewhere here. Sini lah. Okay, darab lagi dengan T, which is 6.3072 10. Okay, so activity at T equal to that value there is 1.7328 times 10 to the power of 5 becquerel. Okay, so that is example 5. Now let's look at example 6. So for example 6, we have a sample of radioisotope which has a half-life of 8.04 days. So half-life there 8.04 days. I'm gonna convert it into seconds. This is I like it in seconds. I'm just gonna see first. Wait, yeah, I'll prefer to do it in seconds. So, ada ka dia minta? Tidak ba dia minta dalam days ka pa ka? Okay, so this is 8.04 days. 1 day is 24 hours. 60. So I have to calculate this. 8.04 times 24 times 60 times 60. So you will get 694.656 seconds. Okay, lepas tu dia minta how much time has elapsed between the two measurements. First, we have the activity at T equal to 0 is 5 millicurie. So we have to convert this into SI unit, so that is 3.7 times 10 to the power of 10 becquerel. So that is 10 185 times 10 to the power of negative 6 becquerel. Actually, let me just double check. I actually don't remember. Yes, 3.7 times 10 to the power of 10. Yes, it's correct. And so we have to find what? We have to find T. Okay, so we have to find the time, because after that it has reduced to 4.2 millicurie. So we have to convert this. 4.2, negative 3, 3.7, 10. 155. So this is the reduce in value. In the activity has reduced, but we have to find how much time for the activity to reduce sampai di sini. Okay, so what we can do is we are going to use A and note E negative lambda T. However, we do not have the value of lambda, so we are going to find lambda. So lambda, we can use the half-life in your formula. So this is ln 2 over T half, which is 694,656. Okay, so, ew, that's so ugly. Okay, ln 2 divided by 656. That is, wait, why did I get a negative value? Decay constant. It should be correct, right? Let me just use my other calculator. Ln 2 624. Oh, salah. Kenapa ni calculator yang satu salah ni? So weird. Yalah. Sian calculator saya. Okay, so I'm using a new one. So this is, should I round it off? 9.98. No, I'm just gonna use 9.98 times 10 to the power of negative 7. This is in per second, right? Did I write it wrongly? Japa, sorry for the delay. Oh, betul lah. Okay, so dapat sudah kita punya decay constant. Then we can substitute into here, but we are looking for T, so I'm just gonna let T be the subject. So that is A naught, E negative lambda T. So ln both sides so that we can remove supaya kita boleh letak this one di depan. Macam itulah. Ln E negative lambda T. So ln E is gonna be equal to 1. So this will be ln A over A naught. This is negative lambda T. So we are looking for T. So this is ln A naught negative lambda. Okay. Kenapa saya suka buat gitu sudah. Right. So this is A berapa? A 155. Kalau kamu mau letak 10 negatif 6 tu pun tulis je lah, mana tahu. Sorry, bless me. Okay, so divide dengan negative 9.98 10 negative 7. So kamu akan dapat the time. Aduh, cepat. Let me calculate it first. 185 divide 9.98 negative 7. So you will get 177,285 seconds. Okay? Yay! Dapatlah jawapan. Jap. 24. Sama juga lah. Okay, so that is example 6. Next, example 7. So we have a radioactive sample contains 3.5 micro gram of pure carbon, which has a half-life of 20.4 minutes. Okay, 20.4 minutes. Determine the number of nuclei in the sample at t equal to 0 seconds. So number of nuclei in the sample. So we are looking for end node. So how do we find end node when we are only given this here? Okay, so how do we solve this is we are gonna use our knowledge in chemistry. Okay, so chemistry, how do we find the number of nuclei in a sample is we are gonna times moles times with the Avogadro constant, right? We have to times that. But how do we find moles? Moles is mass over the molar mass times with Avogadro constant. Okay, so that is 3.5 times 10 to the power of -6. So what is the molar mass? It is 11, atomic mass, which is 11, times with 6.022 times 10 to the power of 23. So that is the number of nuclei. Let me just calculate it quickly. 3.5, -6, 11 times 6.022, 23. Okay, so we'll get 1.916 times 10 to the power 17 nuclei. Okay, so that is A. What is the activity in becquerel of the sample initially and after 8 hours? After 8 hours. So it is in hours, so I'm just going to convert it into seconds. So 8 times 60 times 60 is 28800 seconds. Okay, so activity is A equal to initially and after. Initially and after. Okay, so activity is A naught E negative lambda T. Okay, so sekarang ni kita tahu the initial activity can calculate using this equation here. However, we do not have the decay constant. So decay constant ni kita akan guna the half-life. Ln 2 over lambda. So lambda is ln 2 over half-life, which is 20.4 minutes. So I'm just going to times it with 60. So 20.4 times 60 is 1224 seconds. So this is 1224. So we'll get the decay constant to be equal to 5.66 times 10 negative 4 per second. Okay, so that is the decay constant. So lepas dapat decay constant, kita boleh cari the initial activity. 5.66 times 10 negative 4. This is 1.916 10 negative 17. Okay, 5.66 negative 4 times 1.916 negative 17. So you'll get the initial activity to be 1.084456 times 10 negative 20. Wait, do I need to write that long? Let's just write it lah. Kan? Siapa ya lah? Macam terlalu panjang pula. 845 je lah. Negative 20. 10 kuasa 20 lah. Kejap. Why did I get a different value? Negative 20. Cepat. Let me just check. 5.66. Okay, dapat sama. 5.66. Tapi dia punya decimal banyak bah. Panjang. Ours is not. Let me just 916. Negative. Oh, bukan negative ba pula? Patutlah salah. Kenapa saya taruh negatif di sini? 17. Okay, so it should be correct now. So you'll get 14. 1.0844. Okay, ngam ni. Activity, so dalam becquerel. And then the final activity after 8 hours is just, we are just gonna use this one, 1.0845, and then E negative lambda is 5.66, 10 negative 4, 8 hours, 28800. Right, so 1.0845, 14, E negative 5.66 negative 4, 28800. Okay, so you will get 9. Wow, it's so different. Decimal point dia berbeza terus dapat line betul. But it shouldn't be an issue. So it's going to be 9.034 times 10 to the power of 6 becquerel. Okay, so if tadi di sini kamu guna if di sini kamu ambil 4 decimal point, you should get 8.9 something lah. But this one saya pergi letak, should I use, I guess I'm just gonna kerja pa. Yeah, I think I'm gonna redo this one. So it's gonna be lambda 5.6630 times 10 to the power of negative 4 per second. So what I did is I'm gonna add a much longer decimal point just so that kita punya answer ni tidak terround off, tidak terlalu round off. Sebab sekarang ni saya punya decay constant ada 2 decimal point, but then the rest of my number ada 3 atau 4 decimal point. So kalau boleh kita kasih balance lah the number of decimal point tu. So kira balik 5.6630 negative 4, 1.916, 17. So you'll get 1.085. That's still different though. My god, I'm sorry guys, I'm just tiap pala kita guna je yang ni. 1.085 times 10 to the power of 14, and then A is 1.085 times 10 to the power of 14. E negative lambda is 5.6630 negative 4. T is 28800. So 1.085 14. Tapi in exam nanti dia ada range of acceptable answers juga. So dia tidak salah pun, cuma terlampau round off lah tu. Macam tu lah. Okay, but this one is better. So this one you'll get 8.96 lah times 10 to the power of 6. If you want 4 decimal points, you can take 4 decimal points lah. 8.9 darab 10.6 becquerel. Okay, so dapatlah jawapan dia. Okay, lepas tu calculate the number of radioactive nuclei remaining after 8 hours. Right, so that is just A equal to lambda n. So n is just A over lambda. So this is A. Activity kita tadi 8.9605 10.6. This is 5.6630 10 negative 4. So this will be equal to 5.6630 negative 4. You will get 1.5823 times 10 to the power of 10 nuclei. Okay, so that is the solution for example 7. So basically, kalau kamu punya round off tu kan, make sure yang kiranya diorang akan tengok yang inilah. Kalau 10 kosong 15, dia automatic salah lah. Kalau dia just by a few points, macam 8.98 ka di situ, dia tak kisah sangat lah. Okay, but that's all for example 7. And then let's look at example 7. 5, 6, 7. And then this one should be 8. Example 8. Example 8. So we have a carbon dating on a human remains shows the activity of carbon 14 is per gram of carbon. Oh my god, wait. The initial activity of carbon is, and the half-life. Calculate the age of the remains. Okay. So basically, the original activity of the carbon is 0.231 becquerel per gram. Dia cakap sana per gram. Lepas tu, the remainings is 0.068 becquerel per gram. Okay, so the half-life is given as 5,730 years. Okay, so kita perlu cari apa ni? Kita perlu cari age of the remains. So age of the remains kita akan guna A naught, E negative lambda, T. So kita perlu cari T lah di sini. Tapi sekarang ni kita tiada value lambda. Dua ni kita ada. So again kita akan guna half-life. Ln 2 over lambda. So lambda is equal to ln 2 over T half, which is are we gonna use years? I guess we're gonna use years. Okay, so 5,730 years. So the decay constant is equal to 1.2097 times 10 negative 4 years per year. Okay, so masukkanlah dalam this no, not substitute. We are gonna create the equation for T dulu. So this is A naught lambda T. So ln both sides. Ln E negative lambda T. So this will be ln A over A naught. This is negative lambda T. So T will become ln A over A naught divided by negative decay constant. Okay, so T is equal to ln okay, so we don't have to convert the units sebab nanti dia akan cancel each other. So this is 0.068 divided by 0.231 divided by negative 1.2097 10 negative 4. So the time, the age of the remains is actually equal to 10. Oh my god, that's a lot of number, but 109.2007 years. Okay, so that is the answer for example 8. So basically I think you just have to write down semua the number kalau nampak di calculator lah yang final answer tu. Okay, tapi yang di atas-atas ni at least ada 4 lah decimal point. At least 4 ataupun 5 macam tu. Kan kalau 8 tambah panjang pula. 5 lah, kamu ambil 5 to be safe. Okay, alright, so that's all for subtopic number 2, which is on radioactivity.